a few derivatives to see the pattern. So let's start with function sine x, and I'm going to say n equals 1 because we differentiate the first time. So when n equals 1, differentiating the first time because we're going to get to n equals 87 eventually. So n equals 1 sine prime is cosine x. Would you agree with that?
I agree with that.
When n equals 2, I have to differentiate cosine now prime, which will be the second derivative. So this is the second. I'm going to write the second derivative first. So second is cosine prime, which is negative sine x. When n equals 3, then we have sine x to the third, derivative, differentiated the third time. So I have to differentiate this now. So this becomes negative cosine x. Now, for n equals 4, I can write sine x differentiated 4 times, and then 5. But then after some point, let's say I get differentiated the 10th time, differentiated the 11th time. So we no longer use normal Roman letters, digits. We go back, put in parentheses, 10, 11, 9, whatever. So I just want you to see that if you see at the beginning 1, differentiate the first, the second, the third, the fourth, the fifth, and then all of a sudden you see parentheses 10, parentheses 11, this is what it means. It means that this is the derivative, the 10th derivative, and this is the 11th derivative, and so on and so forth. Okay, so let's take a look. So when n is 1, differentiate the first time, we get cosine. For the second time, we get negative sine x, because that's what I'm differentiating now. Now I'm differentiating this to get negative cosine x, and then I differentiate negative cosine x to get back sine x. So this is the pattern. So if we go to n equals 5, then the sine x differentiated the 5th time, this will be cosine x. So I'm back to this. So everything repeats in blocks of 4, in sets of 4. So cosine, negative cosine, sine. Cosine, negative cosine, sine. Cosine, negative cosine, sine. So on and so forth. So if this is 4 and the next one is 8, so now we are interested in seeing which one is 87. Is it the first, is it the second, the third, or the fourth? Must be one of these. So if we divide 87 by 4, what do we get? So 87 divided by 4, I got 21, correct?
21 dot.
Right, yes, so it's 21 and 3/4, correct? I don't need the dots, I need the mixed number. Is that correct? Right?
Yes.
Okay, so if 21, it's 1, 2, 3, 4, and 21 will be this, 22 will be this, 23 will be this. So 21, 22, 23, so that's the next one, the third one. So it should be this. Because 22, 20, right? So 21, 22, 23. So this would be actually 87, right? So it would be 84, 84, 85, 86, 87. So this is number 87. Luckily, they repeat in sets of 4. Does it make sense?
Yes, it does.
Any questions on this?
No, I understand.
Okay. So this would be basically 84. 84 is here, 85, 86, 87, and 88. And then we continue with 89. Because it's 1, 2, 3, 4, and then this is 5. you. Very good question. Anything else?
It's my last question.
Very good.
It's from section 3.10,
Yes.
linear approximation,
Yes.
and it is using a linear approximation for differentials.
Differentials,
Significant
yes.
Number,
Yep.
radical 102.
Like this?
Oh, I'm sorry, 100.2. That's my bad.
Like this?
Yes.
Perfect. So remember, we always start with that dy approximately dx, the delta y approximately dy. So this will be the f of x plus a little bit minus f of x. I keep writing this so you can get used to it. So this is f prime of x dx. So remember, dy is not the derivative of the function, but the differential of the function. And then I move f of x in front. Hold on 1 second, my other computer just stopped. Okay, now it's working. Okay, so then f of x plus dx is approximately f of x plus f prime of x dx. And this is all I need. This is this. I need to identify the function, I need to identify x, I need to identify dx, and of course after that I will find f prime. So the whole problem reduces to these three. And then I just plug them in. Can everyone see, please? Is this okay? Can you follow?
Yes.
Okay. Stop me if something is not clear, okay? Okay, I'm happy to see Kiki. Kiki's back with us. Thank you, Kiki. Okay, so f of x.
Hello.
Hello.
Radical x.
That's it. X.
It's 100.
Excellent. Careful. Dx.
That is 1 divided by 2 radical x.
So this one, but I want to find dx. That's correct. F prime is indeed 1 over 2 the square root of x, but I want dx.
0.2.
Very good. We're done, right? We just have to plug it in. So f of x with this f of x and with this x, what do I get for this?
10.
Perfect. I have plus. This is 1 over 2. But what is the square root of x?
1 divided by 20.
Yes. Excellent. Times 0.2. So this is 10 plus. I will multiply top and bottom by 10. So it's 2 over 200 or 1 over 100. All I have to do is multiply by 10 and add 1. You don't have to do anything else, but you have to check just to make sure that there is no error. So I will determine the square root of 100.2 and press enter, and I will determine, which I know. I know this is, I don't have to do anything, but I know that this is 10.01. I don't have to plug it in the calculator. So we got 10.009995, which is the exact, and we know that this is not identical. It's approximate. And we got 10.01. So 10.009995 versus 10.01. It's a very good approximation. Sean, is this okay?
Yes, it is.
Other questions? Very good questions. Your questions are always very good.
No, that's it for me today.
And they're helping very much. Any questions on this?
Did you confirm you're going to be changing the test date at all?
I emailed everyone about the 12th.
Okay, I must have missed the I saw the asking what her preference was, but I guess I didn't see the response.
Oh, I'm sorry. Nobody said no for the 12th, so I will keep it on the 12th.
Okay.
Is that okay with everyone?
Yes.
Okay, perfect.
Will that include both classes that are running?
Yes, I probably will do that, yeah, for both classes. Yeah. Good, next question. Is there anything else before we start chapter 4? Anything else for me? Anyone? Anything? Okay, then chapter 4. So in chapter 2, we talked about limits. In chapter 3, we talked about derivatives. And the process called differentiation. Obviously, what we covered today or this week will not be on the test. So this is for test 3. Is that clear, everyone? Yes?
Yes.
Okay. Now in chapter 4, we are going to look at applications of derivatives or differentiation. So this was the basic, then we built on the limits to determine the derivatives, and now we're going to apply derivatives in applications. Applications of differentiation. Okay, our first step is to talk about what is called maximum and minimum, which we have discussed several times before, but there are some details to discuss here. Okay, so in 4.1 max min, so let's take a look at the following function. Maybe I should just look at a graph. But you may not be able to see it. Okay, let's discuss on these graphs. Oops. Let's discuss on these graphs, and then I will definitely graph one. Can you see? Can you see any of these 3, 4, 5, or 6?
I can see 3 and 4.
Okay, perfect. Let's choose one. Which one you would like to discuss? And then I'll graph something and put it in writing for you.
How about number 4?
Number 4. Perfect. So in number 4, I see that this function has what is called an absolute minimum. There is no value that is lower than this. This is the absolute minimum, and this point is at the end point of the interval. Nothing else follows to the left. This point gives the absolute minimum of the function, not a local minimum. Absolute because it's the lowest, but why not local? Because the function does not exist on this side. I'll explain what local means and the difference. But the function does not exist on this side, so this is only global or absolute. Now, this point up here is a point that does not represent a local minimum, right? It's a local max, because I can show that the function exists on both sides and all function values are smaller than this one. So this is a local max. Local because the function exists on both sides and all function values left and right, right here, are smaller than this value. So this is local, this is absolute. minimum, maximum. This one, is this a local minimum? No, it's not a local minimum, but can it be considered a local maximum? No, because the function on this side is, all function values are smaller than this, but on this side are bigger than this. So this point is nothing. It's not a local max, because this point does not exist. And this is not a local min, because all functions value, left and right, have to be smaller than it. So this is nothing. What about this point? This is a local minimum, because the function exists. Is not an absolute minimum, because there is a smaller one, but it's a local minimum because the function values exist left and right and are bigger than it. This one is not only the absolute for this function, absolute or global maximum, but it's also a local maximum because all function values left and right, I can show the open interval, all function values are smaller than it. So this is absolute and local. This one is nothing. It's not the absolute min, and the function does not exist on this side, therefore it will not be a local. Nothing, nothing, local, not absolute, absolute max and local max, absolute min. So now let's differentiate. We saw this graph. I'm trying to keep this computer on. They told us to when we got out last day. They told me to take my computer at home, and I did, my laptop. But now my laptop, if I'm not careful, it just logs me out. I don't understand all this. Why it does that? And it does not. It does not. Sorry about that. Just 1 second. It does not continue to upload. It just goes on some sort of. Sorry about that. I don't understand why it's doing it. Okay, it says welcome. Okay, it's still uploading. Can you believe it? Okay. So let's look at a function, just a simple function for now, but it's defined on a closed interval. This point is the absolute min, because there is no other value smaller than it for this function. This, somewhere here, is a local max, because the function values are smaller than this one. Of course, this will be a local min, and this will be an absolute, not local, max. Endpoints cannot be local. Endpoints cannot be local, max, or min. Why? I cannot show the open interval. The function doesn't exist on this side. I cannot show the open interval. The function does not exist on that side. What happens, what can you say about what happens at this point, which you cannot say here, and you cannot say here? You have to say, or hopefully we understand, that the tangent at this point has a slope that is 0. The tangent at this point also has a slope that is 0. But what do we know about the tangent? What is the tangent? The tangent is nothing else but the derivative. So I would like to go to page, hopefully you have your book, if not it's okay. So Do you think we need to look at another graph, or is the idea clear? Just tell me whether we need to look at another graph. Or we understand how to, from a graph, how to read the absolute max, absolute min, local max, local min. We use interchangeably, thank you. We use interchangeably local or relative. They mean the same thing. Local max min or relative max min, same thing. We use absolute max or global max. So absolute and global mean the same thing. Okay. Let's talk about, before we choose problems, critical numbers. Critical numbers. What is a critical number? Well, a critical number is a point at which so they are points at which one of the following can happen. F prime of x is 0, or f prime of x is undefined for x for which f of x is defined. I'll give plenty of examples, but let's talk about this for 1 second. Oops, sorry. So a critical number, or a function, has a critical number if at a particular x value f prime of x is 0, or, not both, f prime of x is undefined, it does not exist, but for a function value, for an x, that the function is defined. So in other words, a function cannot have a critical number when the derivative is undefined and it itself is not defined. It's not possible. So a function has a critical number where it's defined and at the same time the derivative is undefined. Or it has a critical number where f prime of x is 0. So why are these critical numbers so important? Note, only critical numbers can turn into max min for a function. If a function does not have any critical numbers, it will not have a max or a min. So now we can pick, and you can pick, of course, as well. I'm looking at page 281. I'll pick one, you pick one. Let's say 36. In problem 36, we're only asked to find the critical numbers of the function. So the function is h of p. Okay, finally a video is done, so let me upload the second one from the previous class, believe it or not. Let me just get it started. It's video 10, okay. It's working on it now. Okay, so h of p is p minus 1 over p squared plus 4. Can anyone identify the domain of this function? We are asked to find the critical numbers. Find critical numbers for h of p. But I'd like to identify the domain first before I continue. what will be the domain of this function?
Negative infinity to, oh, yeah, negative infinity to -2, right?
Let's check. The only problem we can run into is the denominator to be 0. Correct?
Right.
Good. So this is a positive number forever. This is a positive number forever. When I add two positive numbers, can I ever get 0?
Oh, no.
No. So luckily, there is no headache here. The function exists for anything. Good. So we're asked to find critical numbers. Critical numbers can come from two possible sources, either from f prime being 0, or if f prime happens to be undefined where the function is defined, that will be another critical number. It can have critical numbers coming from both, coming from one and not from the other, coming from one or not the other, or not at all. But I have to check both and make sure that I have this in the back of my mind. I have to check this and I have to check this. So what would be our first step towards finding critical numbers for this function, if it has any? What do we think we have to find first?
The derivative.
Exactly. Very good. So let's find h prime of p. Watch me run out of room. No, I don't think it's going to happen on this one. Okay, so I differentiate using the quotient rule. So I have to have p squared plus 4 squared in the denominator. I differentiate the numerator and I get 1 times p squared plus 4. I have to write minus. I have to copy p minus 1, but I have to multiply by the derivative of the denominator, which is 2p. Any questions so far? Is this okay? Please stop me anytime. With your permission, I will probably break up the video into 3 smaller videos, only because it takes like forever to upload. Is that okay? Would you mind? And I'll post those for both classes. Is that okay?
Whatever works best for you.
Okay. Okay. I just want to be able to upload them for you. So okay. So any questions on this? Is it okay? Okay, I'm assuming that you're with me. So we'll continue. P squared plus 4. I distribute 2p. I distribute 2p over p squared plus 4 squared. So minus 2p squared will plus 2p. So combine like terms, I have negative p squared plus 2p and plus 4. Everything divided by p squared plus 4 squared. And now you see why we need to do this and simplify it fully. Any questions? Okay, so we know that critical numbers come, as I said, from two sources. Either h prime of p is 0, or h prime of p is undefined, where the function is defined. But let's start with the second one. Is this function ever undefined?
No.
No. So that's not a source of critical numbers. So the only possibility is when I set this equation, derivative, the derivative equal to 0, when is a fraction 0?
When the numerator is 0.
Excellent. So all I have to do is this. Solve the equation. It's not factorable. My only hope is the quadratic formula. Negative b plus or yes, any questions? Negative b plus or minus square root of b squared minus 4 times 1 times negative 4. I don't like to put too many parentheses, so I'm going to do this over 2a. So now grab the calculator. I can let you finish this one, and these are the two critical numbers. We don't know whether they turn into max min or not, and we should analyze them. So let's just evaluate this then. I mean, I can simplify it, but I still have to approximate, so no problem there. So 2 plus the square root of 4 plus 16, oops, close the parenthesis, don't forget to go outside and divide by 2. So 2 plus 4 plus 16, that's the square root of 20 divided by 2, and the other one with minus. So we have two solutions. I got that P is approximately 3.24 and P is approximately negative 1.24. The problem is not asking us to continue. The problem is only asking us to find the critical numbers, and we did. No critical numbers come from h prime being undefined, and we have two critical numbers coming from h prime being 0. Now the question is, are they max min? I don't know. So in case we want to determine that, and I'm anticipating what will follow in this chapter, let's just do that. P, no restrictions on this function. We already established its domain. Let's put h prime of P, and let's also put h of P. We determined two critical numbers, negative 1.24, 0 is somewhere in the middle, and 3.24, and we know that, and we established that the first derivative is 0 at this point. H prime of P is 0, where at 3.24 and the negative 1.24, they are 0. I can determine these values by plugging them in the function. So let's put the function in and determine those values. So the function was P minus 1. Of course, I don't have P in the calculator, so clear whatever else you have in there. So in parentheses for the top, x minus 1, divide by, stop me if you fall behind or you need help, please. So P squared and plus 4, close the parenthesis. And then I go to second and table. I don't want to go too fast. If I am too fast, let me know. Second and table. And I'm going to plug in these numbers. Negative 1.24 and 3.24. And I got negative 0.41 approximately and 0.15. Okay, what now? I go back and look at the derivative. I'm going to copy the derivative here because I don't want to go back there. Okay, so what I'm trying to do next is study the sign of this function between negative infinity and the first critical number. Which function? The derivative. Between negative infinity and the first critical number, and between the first critical number and the second critical number, and between the second critical number and infinity. What is the sign of this piece, no matter what? Perfect. So I don't care about this. I'm going to look at this. And if I plug in 0 to find the sign, 0, 0, -4 times -1 will be, in between the two critical numbers, the sign of the derivative is 0, 0, -1 times -4, and that is?
Positive.
Very good. It's a quadratic function with a negative leading coefficient. It has to look like this. It has to look like this. So it's negative, positive, and negative. Because I don't care about this, it's always positive. So if it's positive between its solutions, it must be negative outside. And you can check with any number. If you plug in -10 in this, you're going to get a negative number. If you plug in +10 in here, you're going to get a negative number, guaranteed. Okay, so now what I would like to analyze is this. Stop me if you have questions. Yes, Jed, you had a question? Anyone? I just want to establish what this point represents and this point represents. Look at the derivative. The derivative is negative. In other words, the slope to the graph of p, h of p, is negative. If the slope is negative, what does the function do? When the slope is negative?
Decreases.
Of course. So this must, from whatever, decrease to this point. Now the slope is positive. If the slope is positive, what does the function do?
Increases.
Yes. So whenever the derivative, which is the slope of the tangent to the curve, is negative, the function decreases. Whenever the slope of the tangent, in other words, the derivative is positive, the function is increasing, always. This is what it's called the first derivative test. So if the first derivative is negative, function decreases. So the first derivative test says this. If we have negative for the derivative, maybe 0 or undefined, I don't know, and then positive, the first derivative test says this must be what type of point? If the slope is first negative and then positive, and if at this point the function either has a 0 tangent or is undefined tangent, what type of point is this?
A local minimum.
Local min. Very good. That's what the first derivative test is saying. What if I have this sequence, either 0 or undefined, not both, and negative? What does the first derivative test say? This means this. So first the slope is positive, then the slope is 0 or undefined, and then the slope is negative. What type of point will this be? What about this situation? Or this situation? Or undefined? What is this?
Nothing.
Nothing. So, of course, these happen only at critical numbers. That's why I said the derivative is 0 or undefined, the derivative is 0 or undefined, the derivative is 0 or undefined, 0 or undefined. So finally, coming back so we can finish up this problem, I added on to it. We were not asked to do all this. What type of point is negative 1.24 comma negative 0.41?
Absolute minimum.
I wouldn't say that. I would definitely say local.
Local.
We have to look at the graph and see, it could be, but we're only interested in local max, local min. What about this point? 3.24 comma 0.15, knowing that this is the sequence of signs for the derivative, meaning the function is increasing because the derivative is positive and then decreasing because the derivative is negative. What kind of point will this be?
Local max.
Perfect. Any questions? Okay, so let's go back and choose something else. Any preference? I have a preference. I see something with exponentials. Like 43 or maybe 44. But we can do a polynomial. You choose. Your turn to choose.
Or you choose